Welcome to Module 9, Digital Image. In this module, we will explore the basic of digital imaging, including raster and vector image format, image digitization, resolution, color depth, and their practical application. These concepts are essential for multimedia and digital media fields. So, digital image refers to creating, manipulating, and storing images in a digital format in a very similar way we have done for sound in previous modules. And for digital imaging, we have two main formats. Raster images, which is the simpler and the most intuitive method to represent digital image. In this format, basically, images are represented as a grid of pixels with each pixel storing color information. So it's the most intuitive. We take an image from the real world and we split it into a grid and we save color information. This representation is called also pictorial or bitmap. And the second one is the vector image. This format abstracts from the pixels using high-level information, like, for instance, lines, curves, shapes, which are defined mathematically, making them resolution-independent and highly flexible. For this reason, it is called also object-oriented format. Let's delve into now the image representation. So, an image can be represented as a signal where the spatial coordinate x and y determine the position, and amplitude c defines the color. So, the mathematical function here is c equal to f, dependent on x and y. This is very similar to what we have seen for audio, where the function was dependent on the time. Here, with the image, we don't have time, but we have the space, and we have the two coordinates. So to process it digitally, we need to digitize the image in both space and amplitude. And we can use two steps. And those steps are the similar steps that we have seen for audio: sampling and quantization. And sampling performs the digitization in space by dividing the image into grid of pixels. Quantization, on the other side, performs the digitization in amplitude by assigning finite amplitude value to each pixel. These processes are similar to audio, but occur in two dimensions. So let's talk about sampling now. So the sampling divides the image into rectangular areas called pixels, and the number of pixels determines the spatial resolution. So, for example, a resolution of 1920 multiplied 1080 means basically 1920 columns and 1080 rows. Of course, the higher is the resolution, the higher is the image ability to show details. In the picture, you can see Lena, an iconic image within the image processing community. And the picture is at different image resolution, so you can actually perceive the difference between them. Image resolution sometimes can also be expressed with respect to physical measures. This is done using DPI, dot or pixel per inch. For example, an image can have a resolution of 300 dpi. This measure mainly is used for printing, where physical dimensions matter. In this case, it is important to mention the pixel ratio, that is the ratio between the width and the height of the pixel. Very often this ratio is equal to 1, which is basically corresponding to a squared pixel. However, in some applications, can be convenient also to use other ratios. There is a relationship between the dimension of the printed image and the DPI. So let's consider an image with a resolution of 633 and 969 pixels, with a resolution of 100 dpi. So the image dimension will be in the real world 16.20 centimeters and 24.61 centimeters. If instead the resolution is 200 dpi, the resulting dimensions in the real world will be 8.1 centimeters and 12.30 centimeters. On the other side, fixing the physical image dimension, higher DPIs means smaller pixel, improving printed image quality. Let's move now to the quantization process. So quantization involves mapping the amplitude value of an image to a finite set of levels, as we have seen before. In image, these amplitudes are related to the wavelength of colors. In grayscale, for example, these levels range from black to white. In this scenario, if we consider a quantization of 5 values, all amplitude values in the analog domain will be mapped in just 5 shades of gray. We define the maximum number of possible colors to assign to a pixel as a color depth. In the aforementioned example, the color depth is 5. The higher is the quantization level, the higher is the color accuracy, but on the other side requires more storage. In the picture, we can see an example of the same image where the resolution is kept constant and we change the quantization levels. The number of rows and the number of columns so remain constant, but a different grayscale color depth. So now let's delve into the color depth definition. The color depth refers to the number of bits used to represent each pixel's color. For example, 1 bit means 2 possible colors. 8-bit allows to have 256 colors. 24 bits allows to have over 16 million colors, which is called also true color. The higher is the color depth, the higher is the quality of the image, but also increases the storage requirement. We can see an example in the table. Color images are formed by combining different color components, such as red, green, and blue in RGB color model. Each component has its pixel matrix, as we can see in the figure, where we can actually see the 3 different matrices. Each component of the color model is quantized and color depth is distributed equally among them. For example, if we have color depth of 24 bits, this means to have 8 bits for each RGB channel. If we have a color depth of 16 bits, this means to have 5 bits for each channel RGB plus 1 that is an unused bit. In this picture, we can see the difference in quality between a colored image with colored 24 bits and one with 4 bits color depth. Let's move now to another paradigm of format for images, vector images. So the vector images are composed of abstract geometric elements like circles, lines, and curves defined mathematically. These images are resolution independent, flexible, and occupy separate layers for easy manipulation. Each geometric entity is modeled using a mathematical formulation, from the most intuitive, for instance, as we said, circle, rectangulars, and lines, to the most complex, like spline or Bezier curves. Each entity occupies its own layer and can overlap with other entities. The position of the object can be changed at will from one layer to another layer. We can easily notice how object-oriented images are very appropriate for image manipulation with respect to other paradigms, like raster. Common uses include logos and illustration. How colors are mapped and managed into the vector images. So vector images support various coloring patterns. Spot color that selects a color in one of the color spaces that we have seen, but also manages shading that allows gradient and directional effect, and then textures that are fixed or parametric patterns for realistic appearance. So let's move to the conclusion. In this module, we explore digital images, focusing on raster and vector formats, digitization process, and key parameters like resolution and color depth. Understanding this principle is crucial for fields like graphic design, multimedia, and digital imaging. Thank you for your attention.